Right, good afternoon everyone. We will continue with our tutorial. So last week we have already covered tutorial chapter 4. We already started on tutorial chapter 4. We have completed question 1 and 2, right? Today we continue lah with the question, right? Question number 3 I will skip, bukannya purposely skip, just that question 3 is homework for you. Okay, as usual, I've already uploaded the questions. The final answer pun dah ada. So question 3 saya sengaja biarkan, saya sengaja tinggal dalam tutorial ni. When you have extra time later or some other days, please attempt question number 3. Okay, so today I will focus question number 4, number 5, number 6. Question number 3 is not too tough, quite straightforward. Kalau kamu faham soalan, you know the equation, you should be able to solve question number 3 without much problem. Okay, so I will cover question 4, 5 and 6 as these questions are somewhat not different, I would say not direct questions. So these questions I would like to explain lah how you are supposed to solve question. Okay, so you know chapter 4 is very challenging in comparison to the other chapters, just because chapter 4 has many equations, and I can understand that sometimes the equations can be overwhelming. Tapi like I said, when you attempt question chapter 4 ni, kamu kena faham, you need to really understand 3 things, meaning whenever you see questions that are related to designs of reactor, the 3 things that you really need to check first. Sebab kalau kamu perasankan chapter 4 we have so many equations, up to 50, 60 equations kan. So it is hard to know which equation nak guna. So that's why you have to remember 3 things. Okay, one is you have to really know the reactor yang design, or in meaning kalau katakan dalam example questions, what reactor that you're going to find the calculation for. Is it batch, is it PFR, or is it CSTR? So that's first thing. Kalau kamu tengok reactor yang salah, memang completely salah lah kan. Okay, so first, types of reactor. Okay, second is the rate law. So you really need to make sure you know the correct rate law based on the questions. Okay, so part ni pun kamu tak boleh salah. So kalau let's say rate law dia is, let's say it's mentioned as minus RA equals to KCA. Tapi kalau katakan kamu tersalah pandang ke, or you interpreted wrongly, let's say you go and see minus RA equals to KCA square, and then confirm salah juga. So completely you have the wrong equation. Second. Third pula, the phase of the reactant, whether it's liquid or gas. So kalau part ni pun kamu kena tengok betul-betul lah. Let's say katakan, if the case of batch reactor, tak apa, different types of phase pun equation dia masih sama. Tapi when it comes to PFR, CSTR, the flow reactors, the difference of phase will give you different equation. So kamu kena tengok betul-betul. So katakan dia adalah gas phase, you go and see, make sure you go and check the equation for gas phase. Kalau dia liquid phase, go and check equation for liquid phase. Okay, so sebab equation memang you don't have to memorize. The pro of it, you don't have to memorize. The cons of it, there are many equations. Sebab tu these 3 things kamu kena make sure. Sebab kalau salah satu daripada 3 ni, you are wrong, definitely you have the wrong equation. Ataupun definitely kamu akan tengok equation yang salah. Kalau ketiga-tiga benda ni kamu tak tengok dengan betul. You have to see, make sure all 3 criteria are correct, then baru you will get the correct equation. Okay, alright. So let us try to go to question number 4. The following liquid phase elementary reaction is to be carried out isothermally with no pressure drop. Okay, so remember kan, when it comes to chapter 4 pula, ada satu lagi tambahan. Okay, katakan if it's a gas phase reaction. Okay, only and only for flow reactor, gas phase reaction, kamu kena check juga, would there be any changes of temperature, would there be any changes of pressure? Okay, so changes of temperature we haven't addressed yet, we will address in chapter 6, but changes of pressure we have already addressed in chapter 4. So kamu kena tengok juga, sebab saya dah senaraikan dah equation apabila there are changes of pressure. Okay, so make sure you also see kalau ada perubahan, there's a change of pressure, what happens to the final equation. So tengok balik note saya. Part yang awal-awal tu, when I derive, I memang tak include change of pressure dulu. Sebab kalau saya include, it be very confusing for U. So that's why bila saya derive, saya tak letak part yang changes of pressure. Tapi kalau kamu tengok selepas tu saya ada address balik, saya ada compile balik semua equation yang akan berubah if there are changes of pressure. So make sure you really know the notes. Okay, part mana bila tak ada perubahan tekanan, part mana yang bila ada perubahan tekanan. Right? Okay, so now this question says, first dia kata liquid phase. So kalau liquid phase reaction ni kamu tak payah bimbang lah pasal change of temperature ke change of pressure pun you don't have to worry. Okay, sebab design equation dia masih sama. So when you see liquid, you should feel better. It's not that, the equation will not be that complicated. Okay, second, elementary reaction. So kamu dah tahu kan, whenever you see the word elementary, meaning to say that the rate law tu akan follow chemical equation dia, or meaning to say the reaction order in the rate law will follow the stoichiometric coefficient of the reactant in the chemical equation. So for example dalam case ni reactant dia A and B, right? So A and B, and in the chemical equation is 1A reacting with 1B. Hence reaction order untuk A is first order, reaction order for B is also first order. So the rate law become minus RA equals to KCA CB. Okay, so as I told you, dalam test ke dalam exam, kamu dah tahu tulis rate law, kamu tulis je dulu rate law dia. Because when you write rate law, so you actually get marks already. So saya selalu cakap kan, you cannot solve, sometimes memang tak boleh solve the whole question. Let's say you are unable to solve, okay je. But if you know something, example kamu baca ni, kamu tahu macam nak tulis rate law dia, tulis je, kamu dah dapat markah. Just by writing the correct rate law from the information, you can already get certain marks. So make sure you do that, right? So that they say, carry out isothermally, meaning no change of temperature and no pressure drop, no change of pressure. Okay, so perhaps, I just address, perhaps some will wonder, kenapa kita always touch on liquid and gas? We don't really touch on solid, if you realize, right? Kan basic reaction mostly we touch liquid and gas. We hardly talk about solid. Why? Because in the normal applications or in the very common industrial processes, it's easier to process liquids and gas in comparison to solid, especially open system. So imagine kalau kita adalah flow system, kan senang. If we want to pump, in terms of pumping, kita nak pump liquid, kita nak pump gas, is so much easier compared if you want to pump solid, right? Sebab tu kalau solid reaction, usually dalam batch reactor, sistem yang tertutup, means saya masuk saya punya solid, then let's say kalau reaction ni dengan liquid, saya campur dalam, saya tutup, reaction takes place. But open system, very rarely lah we have solid reactions. Kalau ada pun dia semi batch, maksudnya solid tu dah masuk dulu, maybe the liquid or gas will be flow in, flow out. So that's why we hardly address solid reaction. If possible, usually the industry will try to melt it into liquid, okay, for easy processing. So that's why you wonder why we hardly talk about solid reaction, mostly because of that, right? Okay, so come back to here. Okay, next dia kata no pressure drop. Okay, so samalah kalau liquid phase, no pressure drop, no temperature change, pressure change will not affect our design equation. Next dia kata reaction rate constant K at 30 is 15 dm³ per mole minute. So they give us the K, but the K is specific at 30 Celsius. Right, so then dia kata with an activation energy of 25 kilojoule per mole. Okay, so you know by now, right? Activation energy itu adalah EA lah. But the EA unit, be very careful sebab most of the time unit energy ni is very big. That's why macam usually in 4 or 5 or 6 figures. So sometimes it's too big to write, let's say 20,000 joule per mole, or let's say 150,000 joule per mole. So normally they will write in terms of kilojoule, kilocalorie. Tapi konsep dia sama je, macam kamu kira meter kepada kilometer, means you times 1,000, right? So kilojoule to joule, you just times 1,000. So ultimately EA dia is actually 25,000 joule per mole. Okay, done. Okay, so you have the information already. Next, let's go to the question. The reaction mixture consists of 60 mole percent A, 60 mole percent B remaining A. Okay, so dalam case ni, because initially we have A and B. Okay, so kamu kena faham dalam real processing, walaupun even though the chemical equation states A akan masuk sama dengan B kan, dalam equation ni kata 1A, 1B. Tapi in the real application, not necessarily your composition yang kamu guna tu akan sama dengan stoichiometric coefficient. So kenapa? Sometimes you might wonder why, right? Okay. I do agree, kalau stoichiometrically, chemically, the reaction will occur between 1A and 1B. Okay, but like I say, sepatutnya kalau ikut chemical equation, dia mesti 50% A, 50% B yang masuk kan. Tapi dalam soalan ni kamu tengok, tak. We have more percent of B in comparison to A. So why? And this is not because of question. Even in real application pun sometimes you will see this. Okay, kenapa? Nanti dalam chapter 7 we will learn. Sometimes when you have reactor, walaupun reaktor yang sama, kadang-kadang boleh berlaku multiple reaction. Sometimes this multiple reaction can be competing reaction. So salah satu cara, sebab bila kita ada competing reaction, akan ada the reaction that we want, sebab tindak 12 tu menghasilkan produk yang kita nak. Tapi at the same time, we cannot avoid competing reaction that might produce our undesired product atau produk yang kita tak nak tapi dia terhasil disebabkan ada multiple reaction. So one way kita nak manipulate ni adalah concentration of our reactant or the mole fraction of our reactant. So that's why we do this is kita nak maximize tindak balas yang kita nak. We call it desired reaction. Kita nak minimize undesired reaction. So one way is to manipulate the composition of your reactant initially. Nanti chapter 7 kamu akan faham kenapa kadang-kadang stoichiometric kata sepatutnya 1A bertindak balas 1B, tapi real application kita tak letak pun 50% A, 50% B. Okay, so just information and knowledge to you, right? So in this question, they says that mole percent ataupun dalam bentuk mole fraction, kena ingat kalau dia dalam bentuk percent, kita when comes to calculation, we calculate in terms of fraction, and this 60% is fraction B, so mole fraction B. So YB not 0.6, YA not 0.4. Okay, sebab hanya ada dua bahan A and B. So if 60% B, naturally 40% A. So YB not 0.6, YA not 0.4. Right, this says determine the initial concentration of A. So they want us to find what? They want to find CA naught. So awal-awal dia kata tak, soalan kata dia nak cari CA naught. If the reaction is carried out in a plug flow reactor, so this is a PFR. Okay, remember I told you tiga benda yang kita kena tahu kan? Satu, PFR, kita dah tahu design reactor, kita dah tahu reactor dia PFR. Second, rate law pun kita dah tahu, minus RA KCACB. Third, this is liquid phase. So berdasarkan tiga maklumat ni, kamu dah tahu macam mana nak cari dalam notes, okay, equation mana yang nak digunakan. So dalam exam dengan test, kamu kena tahu tiga-tiga benda ni. Tak boleh salah satu pun salah pun tak boleh. So dalam kes ni, kamu dah tahu PFR, minus RA, KCACB, and kamu tahu this is liquid phase. Okay, tengok notes, design equation mana untuk specifically untuk ketiga-tiga condition ni. Alright, so dia kata with a space velocity of 1.5 per minute. So dia kata cari CA naught. Dia beri space velocity, okay, as we at 50 Celsius. Okay, so dia beritahu sekarang dia nak cari kepekatan CA naught. Dia want to find CA naught. They give us space velocity 1.5 per minute, and they state that the reaction is at 50 Celsius. Okay, so kamu kena faham pula. Dalam design equation kita, part mana influenced by temperature. Okay, so the only variables or the only part that will be influenced by temperature is K. Maksudnya kalau dalam equation kamu ada K, K tu kamu mesti make sure must be at 50 Celsius. So if you see you use K at any other temperature, dalam design equation kamu dah tak valid. Sebab dalam design equation kita, the only thing affected by temperature will be K. So you dah kena tahu dalam idea, dalam your mind, okay, my K tu kena consistent at 50 Celsius. Okay, then it says 60% conversion. So X to 0.6. Okay, so how do we do this? Okay, in order to do this, right, kalau kamu perasan dalam note saya, ingat tak bila saya I derive the equation, I give you in different form kan, satu equation tu akan jadi different form depending on the information given. So saya kata kadang-kadang ada tiga version. Version pertama, version kedua untuk mencari volume. Version ketiga untuk mencari space time, tau. And then I told you kalau space velocity saya tak letak dalam note, saya minta kamu cari sendiri. Okay, so dalam note saya memang tak ada formula space velocity. Okay, I told you, remember that you have to find by yourself. Okay, so happen soalan ni dia bagi kita space velocity means kita kena derive dulu equation dia lah. Okay, so to derive the equation, of course again kamu kena start daripada design equation, tapi saya cepatkan sikit saya tak terang sangat derivation, tapi saya nak terang macam mana dia menjadi space velocity. Okay, so kalau kamu tengok dalam notes, okay, dalam notes you cari PFR minus RAK CACB liquid phase, design equation dia given as volume PFR equals to V naught per K CA naught in bracket 1 per theta B minus 1 ln theta B minus X theta B 1 minus X. Yang saya tengah highlight ni adalah equation yang memang dah ada dalam note saya. Bukan equation yang baru dalam note saya dah ada. Tapi equation ni untuk mencari volume. Kita nak apa? Kita nak space velocity. Okay. So part ni kamu kena ingat. Dalam chapter 2 chapter 2 we learn about space time, we learn about space velocity lah. Apa beza dia? Kalau space time tau is volume per inlet volumetric flow rate. Okay, again kalau space time volume per inlet volumetric flow rate. Kalau space velocity terbalik je. Volume inlet volumetric flow rate per volume reactor. Okay, so kalau kamu tengok dalam equation ni, right? So kalau saya nak dapat space velocity, apa yang saya kena buat? Saya kena pindah volume PFR ni from left to right. Betul tak? Kalau saya pindah left to right, kalau kat left dia kat atas, kalau pindah ke right dia akan jadi bottom, right? So dia akan menjadi inlet volumetric flow rate per volume PFR. Okay. So kalau dapat volumetric flow rate per volume PFR, dapatlah space velocity, betul tak? Tapi itu dah bahagian kanan. Yang selebihnya sekarang means the other variable kenalah pindah ke bahagian kiri. Sebab kanan saya tinggal volumetric flow rate kepada volumetric flow rate per volume. So the other variables will go to the right hand side, will go to the left hand side. Kalau pergi left hand side, you have to be very careful. Meaning the KCA naught ni daripada bawah pergi ke kiri dia jadi atas kan. So dia dah ke pengatas. Yang bracket besar ni, bracket besar yang dalam bracket tu akan when move to the left hand side, it become per kat bawah. Okay, so this part you have to be very careful kerana student confused sebab yang bracket besar ni dia ada dua, macam ada atas ada bawah guys. So kamu kena ingat dia adalah it comes in one of its own. It comes as its own. Okay, so bila kamu nak pindah, the whole bracket will goes to the bottom. Okay, when you move to the left hand side, it goes to the bottom, and the KCA naught from the bottom will goes to the top. So then you will get the space velocity punya equation. Okay, so this one memang tak ada dalam note saya, tapi kalau kamu ingat dalam lecture saya cakap space velocity, please find time to express it yourself. So tak susah je, tak susah pun, just that kamu kena faham lah, dia just reciprocal sahaja. Okay, alright. So once dah dapat space velocity punya equation, okay, kamu dah kena ingat apa yang kita nak cari kan? Kita nak cari CA naught, kita cari CA naught, meaning expression lain, variable lain semua dah kena cari dahulu. Kamu dah tahu kan kalau mathematic equation, kalau kita dah tahu apa variable yang kita nak cari, okay, dia mesti satu variable je. Satu equation, satu variable. Kamu tak boleh dua variable ataupun lebih daripada satu dalam satu equation, you can never solve it. Okay, so kalau kita dah tahu CA naught yang kita nak cari, means the rest semua kita dah kena tahu dahulu nilai dia. Okay, so firstly, space velocity. So space velocity is given already 1.5 per minute. So space velocity dah settle. Okay, so belah kanan tu saya dah tahu berapa. Okay. Next, K pula. So K yang kamu kena berhati-hati. Sebab tu kadang-kadang dalam rate law, straight away right, K di mana suhu tindak balas saya is was 50 Celsius, right? So 50 Celsius, I convert to Kelvin is 323.15. 50 plus 273.15 is 323.15. So that I know K yang saya nak guna tu mesti K pada reaction temperature. Okay, so in our case, although they are given the K, but the K is at 50 Celsius. K yang given is at 30 Celsius. Sorry, here. The K given in the question is at 30 Celsius. Okay, so This is where your knowledge of reaction engineering comes handy. Means kamu dah kena tahu. Walaupun saya tak, dalam soalan tak suruh mencari K baru kan. Tapi kalau kamu faham konsep, kamu faham perubahan temperature menyebabkan perubahan apa dalam design equation. Naturally, you know that you have to calculate the new K. So this part I always will remind you sebab dalam reaction ni memang very often we will change reaction temperature. Even in the real application, in the real world, temperature ni salah satu parameter yang sering dimanipulasi or manipulated in the system. So you have to understand kalau kita kacau temperature, apa yang dikacau dalam pengiraan. Okay, so K lah, alright. So to calculate new K, I suppose by now kamu dah tahu kan Arrhenius equation. I suppose by now you already know how to calculate the new K. So make sure you know. And the new K at 50 Celsius is 27.71. So done. So first part dah cari nilai K yang baru. Okay, down. Bottom pula, theta B. Okay, so theta B pun is nothing new kan. Theta B kamu dah pernah carikan dalam chapter 3. We have learned finding theta B. So theta B tu apa? Theta B kalau kamu forget, it's always simple understanding initial amount of B over initial amount of A. So amount ni berada dalam bentuk fraction, concentration, molar flow rate, so on and so forth. Tapi yang penting konsep dia mesti nisbah asal bahan B terhadap nisbah asal bahan A. In this case, they give us in terms of fraction. So kita gunalah kan YB0 0.6, YA0 0.4. So you will get theta B 1.5. So done on theta B. So next one X. So X pun dah diberi 60%, 0.6. Don't forget. Dalam pengiraan sebarang peratusan, not only in chemical, not only in reaction, any other mathematics pun sama je dalam persamaan. Sebarang pengiraan melibatkan peratusan. Bila kamu nak kira, you have to change into fraction. So the X change into 0.6. Okay, so when you calculated as shown here, alright, as shown the bottom here, you should be able to get the initial concentration as 0.044 mole per dm cube. So this is how you calculate the solution for question number 4A. Not that difficult, but mungkin one thing that you might have challenge nak derive equation untuk space velocity. Like I said, dalam note saya tak tunjuk untuk space velocity. So make sure you do it first before test ke before exam ke, kalau just in case dia keluar dalam test ataupun dalam exam. Okay, so done on question number 4A. I will go to the next question, 4B. Okay, so question 4B. In order to increase the conversion of A to 90% from part A above. Okay, so soalan ni kata, tadi in the first question, kita dah capai conversion 60%. Okay, conversion pertama 60%. Dia kata sekarang conversion 60% tu dah tak cukup, it's not enough. So they want to increase the conversion to 90%. Okay, so dia kata a continuous stir tank reactor with a space velocity of 0.42 per minute is used in series. So sekarang dia kata kita andaikan, katakan dalam part pertama tu, first reactor tu baru 60%, tak cukup, right? So part B dia kata kita nak increase conversion kepada 90%, and what we do, we connect from the first reactor to the second reactor, which is now a CSTR. Okay, so dia mungkin sebelum ni bila saya ajar kamu bersiri, saya selalu ajar kamu bersiri reaktor jenis yang sama kan, maknanya CSTR, CSTR, PFR, PFR. Okay, nampak ni pelik sikit lah, tapi okey je, dia takkan mengacau pengiraan kita. Walaupun dalam soalan ni macam pelik lah, PFR tiba-tiba sambung CSTR. It's a bit weird lah kan, in the real industry. Okay, tapi kalau just andaikan sekarang yang CSTR yang kedua ni is connected in series to the first reactor, and the second CSTR ni will convert from X1 0.6 to X2 0.9. Itu yang penting. Yang kita nak tahu penting untuk maklumat dia adalah sebenarnya nak tahu dia adalah CSTR. Second, dia beri kita space time CSTR 2 kita ni. Our second CSTR space velocity 0.42 per minute. Still space velocity. And the conversion lah from X1 0.6 to X2 0.9. As a result, the initial mole percent of reactant A and B must be changed. Jadi kata disebabkan kita nak naikkan conversion, kita sambung kepada reaktor yang kedua, which is a CSTR, with a space velocity 0.42 per minute. Okay, disebabkan kita nak capai keadaan ni, mole percent A and B tu harus diubah. So maksudnya sekarang tadi yang YA0 0.6, YB0 0.6, YA0 yang 0.5 tu harus diubah. Kita tak boleh guna YB0 0.6, YA0 0.4. So this is determine the new initial mole percent of reactant A and B using the initial concentration of A and the reaction rate constant obtained in part A above. So dia kata sekarang dia suruh kita cari YA0 yang baru, YB0 yang baru, okay, menggunakan CA0 from part 1 and K from part 1. Okay, so that's the question that they want. Okay, so let's say kamu tak sure sebenarnya dia nak suruh kita kira apa. Okay, kadang-kadang macam ni dalam soalan ke ataupun later when you go to work also, when you have problem, sometimes kita tak tahu apa yang kita nak solve. In some ways I can say it that way. We don't know what we want to solve. Or sometimes we know what to solve, we don't know where to start or what to do first. Okay, so kamu kena ingat je first. When it comes to, of course not in all situation lah kan. Okay, but in this situation, you must first know apa equation yang related ataupun apa benda yang akan related dengan benda baru yang kamu nak cari ini. Okay, so in this our case, kita tahu sebab dia beri kita space velocity. Kalau dia beri kita space velocity ke, volume ke, space time ke, kamu tahu dia berkaitan dengan design equation. Okay, dalam chapter 4, kamu tahu space velocity ke, space time ke, volume reactor ke, dia mesti berkait dengan equation, design equation kita. So first thing we do, kita cari dulu design equation dia, dan kita figure out daripada design equation tu apa benda yang boleh berubah atau apa benda yang kita boleh kira untuk solve masalah dia. Okay. So to do this, to begin this, kamu dah kena faham pula dalam notes chapter 4 saya, kalau kamu ingat, saya tak ajar untuk reactor, saya hanya ajar single reactor. Dalam chapter 4, kalau kamu ingat saya derive equation, saya hanya derive untuk single reactor. I didn't derive for reactor in series. However, ada however pula kan, dalam chapter 2, saya pernah ajar. Okay, so bagaimana kita nak relate these two. Okay, sebetulnya kan reaction ni, dia punya chapter ni bukan in silo. In silo ni means chapter ni bukan isolated on its own. Actually, all the chapters are related to one another. So means sometimes you're attempting question chapter 4, but the knowledge comes from chapter 2 or chapter 3 yang kamu kena combine. Okay, apa maksudnya? Okay, saya beri contoh dalam case ni. Yes, kamu tak belajar macam nak derive equation untuk reactor berseries. But you learn in chapter 2. Okay, apa yang kamu belajar dalam chapter 2? Kamu belajar volume for second reactor dalam chapter 2 akan sama dengan FA0, reactor second reactor. Okay, FA0 X2 minus X1 per minus RA. Kalau kamu ingat, kamu belajar dalam chapter 2, dia akan jadi per minus RA. Okay, sebab kenapa kita, dan dalam chapter 2, nilai minus RE itu dah diberi directly, ingat tak? Kita tahu conversion, dia terus beri kita nilai minus RE. Okay, so dalam chapter 4 dah tak boleh sebab nilai minus RE itu tak diberi directly. But kamu dah belajar dalam chapter 3, rate law pula. Okay, sebab tu kamu kena combine. Okay, what do we mean by combining? Alright. Since chapter 2 says, volume CSTR sama dengan FA0 in bracket X2 minus X1 per minus RA2. So, kamu sekarang carilah minus RA2. So, how to find minus RA2? Okay, kenapa saya cakap minus RA2? Sebab this rate of reaction occurs in the second reactor. Okay, so kalau bagus second reactor, kita nak senangkan pemahaman, kita tulis minus RA2. So, macam mana kita nak tulis rate law dia? Okay, kamu kena faham rate law dia masih sama, meaning still first order with respect to A, first order with respect to B. Tetapi kamu kena faham, dia first order with respect to A, first order with respect to B in terms of concentration kan. Tapi concentration ni, bila kita ada dua reactor, kamu dah kena faham, dia merujuk kepada concentration reactor 1 or reactor 2. Since we are talking about rate of reaction in the second reactor, hence the concentration must refer to concentration of A and B in the second reactor. Sebab tu saya akan tulis rate law dia sebagai K CA2 CB2. Okay, dah. Kalau tadi soalan pertama tu KCACB kan? Okay, maknanya dia refer kepada reaktan pertama sajalah sebab tak ada reaktan kedua. Tapi bila ada reaktan kedua, kamu dah kena clearly clarify as KCA2CB2. Means CA2CB2 merujuk kepada its concentration of A and B in the second reactor. Okay, then done. Okay, lepas tu pula sama je konsep. Kita pun kena express kan CA2 and CB2 in terms of CA0 dan X2. Sama je, kita kena express balik concentration dia. So untuk express CA2, kamu dah pernah belajar. Kalau CA sama dengan CA0 in bracket 1 minus X. But now if I talk about concentration in second reactor, CA2 akan sama dengan CA0 in bracket 1 minus X2. So why X2? Sebab this concentration is in the second reactor. It involved the conversion in the second reactor which was 0.9. So itu akan sebagai 1 CA0 1 minus X2. CB2 pun sama. CB2 previously CA0 in bracket theta B minus B per A X. So now CB2 is equals to CA0 in bracket theta B minus B per A X2. Okay, so that's the case. Right, so B per A dalam saya punya example from the chemical reaction, our B per A is 1. So chemetric coefficient untuk B adalah 1. So chemetric coefficient for A is also 1. So B per A become 1. So CB2 becomes CA0 in bracket theta B minus X2. Okay, so kita combine balik. Kita combine, so maknanya yang kat bawah tadi yang KCA2 CB2 become K CA0 in bracket 1 minus X2 multiply with CA0 in bracket theta B minus X2. Okay, so when these you combine, you will get back the equation now becomes volume CSTR second is V0. Saya tukar dalam bentuk V0. Okay, kenapa? Sebab saya nak dalam bentuk space velocity kan. Kalau space velocity mesti dalam bentuk inert volumetric flow rate. So sama je lah konsep dia kan, sebab FA0 di atas divide with CA0 di bawah, you dapat V0. So V0 in bracket X2 minus X1 over divided by K CA0 1 minus X2 theta B minus X2. Do note, equation ni memang tak ada dalam saya punya notes. Dalam notes saya chapter 4, saya hanya address hanya address a single reactor. So means part ni kamu kena betul-betul faham. Chapter 2 kamu kena combine and actually derive by yourself the equation for this. Okay, so hopefully you understand the explanation. Alright. Okay, tapi belum habis lagi sebab equation ni untuk mencari volume. Kita nak space velocity because the information given to us was a space velocity. So sama konsep je lah. Volume, I move from left to right. So this volume CSTR2 pindah daripada kiri ke kanan, dia jadi pembawah. The rest of the variables in my right hand side, I move to the left, sorry. So you will get space velocity for the second CSTR equals to K. Okay, yang bahagian bawah ni, yang kiri bawah, kanan yang bawah ni jadi pengatas. So K CA0 1 minus X2 theta B minus X2 per yang X2 tolak X1 ni akan pindah ke bawah. Kita dah bawa ke sebelah sana kan, kita dapat equation ni. Okay, so now belum lagi selesai. Tapi you somewhat knows, okay, ini design equation yang saya akan guna untuk pengiraan saya. Okay, so dah kamu kena fikirlah. Daripada all the variables here, apa benda yang akan berubah kalau saya tukar mole fraction A dan mole fraction B? Kan sebab dalam soalan kata, dia suruh kita cari YA0 yang baru, YB0 yang baru. So dalam equation ni, kamu kena faham lah. Which one will be affected if I change YA0 and YB0? So if you realize the only thing that will change if I change YA0, YB0 is of course my theta B. Kerana because theta B tu sama dengan apa? YB0 per YA0. So if I change YB0, I change YA0, automatically my theta B will change. Meaning to say, if I can find theta B first, I can find YA0 and YB0. So from this equation kamu dah tahu, the only thing yang akan berubah kalau I change YB0, I change YA0 is theta B. So vice versa, dia punya pemahaman. So kalau saya boleh cari theta B yang baru, I can then find YB0 dan YA0 yang baru. So means from these questions, from this equation, theta B is my unknown. The rest I need to substitute with numbers in order to get theta B dahulu. Okay, so how to get theta B? Okay, right. So space velocity is already given. The second CSTR space velocity is 0.42 per minute. Okay. K from part 1, you don't have to find another K. It was a K from part 1. CA0 pun daripada part 1. Tadi yang kita solve, kita dapat CA0. Kita guna balik sebab dia kata in the question says, using initial concentration and reaction rate constant obtained in part A above. Okay, done. So X2 kita dah tahu 0.9. X1 is 0.6. So we are left with theta B. So when you solve this, you will get theta B as 1.93. Okay, tapi belum satu lagi. Dia bukan nak suruh kita cari theta B kan. Dia nak kita cari YA0 dan YB0. So you have to remember. Theta B tu sama dengan YB0 per YA0. Okay, so kamu pun kena ingat kan. YB0 tambah YA0 sama dengan 1 sebab 100% tu akan merangkumi peratusan A, peratusan B. Ataupun we can say YA0 plus YB0 equals to 1. Hence, YB0 tu sama dengan 1 minus YA0. Sebab kamu kena tengok, kita nak cari, kalau kamu tak faham okay. Kita nak cari YB0 dan YA0. Tapi ingat saya kata kalau satu equation, satu je unknown yang kita boleh solve. Tapi dalam equation ni ada dua unknown. So macam nak buat? So kita tahu perkaitan antara YB0 dengan YA0 sebab kita tahu YB0 plus YA0 equals to 1. So YB0 tu saya tulis dalam bentuk 1 minus YA0. Bawah YA0. So sekarang kamu tengok satu equation, satu unknown. So since I know theta B 1.93 and since my equation only left with YA0, then I can solve my YA0. I will get my YA0 as 0.34, 34%. And then nak cari YB0, 1 minus 0.34, you get your YB0 as 0.66 ataupun, 0.66 or we can call it as 66%. Okay, so done for question part B. Question part B, I admit a bit hard because equation ni memang tak ada dalam note saya. Sebab tu nanti bila kamu ada masa, kamu kena betul-betul venture tengok apa yang berlaku kepada equation kalau dia adalah reaktor bersiri. Bash takkan kenalah. PFR pun takkan. CSTR is PFR dengan bash daripada ni tak ada bersiri lah kan. Bersiri PFR dengan CSTR kan. Tapi PFR bersiri pun tak possible untuk saya tanya lah sebab equation dia integral akan jadi sangat complicated. CSTR bersiri is very possible for me to ask in test or exam. So make sure you know how to derive equation kalau CSTR tu dalam bentuk bersiri for the notes in chapter 4. Right, so done for question number 4. Okay, so I give you about 1 or 2 minute break. Saya pun break kejap. Okay, saya break kejap. I will come back in 1-2 minutes time. Then we will continue to the next question. So if you have, kamu nak tengah mengira pun, you can take the time to calculate. I will come back in about 1 or 2 minutes time. Okay, alright. Right, time is up. So we go to question number 5. Okay, so even if you wonder why sometimes reaction macam soalan tu kompleks atau kenapa macam equation tu kompleks, kamu kena faham kadang-kadang I admit the questions are tough and the notes, bukan notes lah, content tu adalah a little bit complex. Why? It's because saya tak nak just ajar untuk kamu buat, saya tak nak ajar just untuk the purpose of teaching. I have to actually teach you to cover what's common in the industry. Sebab tu macam kalau kamu perasan, I can teach you the basic one. Meaning kalau saya stick kepada basic reaction, basic design equation, definitely you will learn not more than 10 equation. Tapi I find it tak practical sebab nanti bila kamu pergi industri, reactor ni is really the heart of any kind of chemical plant, and you can see macam kamu tengok sekarang memang reactions tu very diverse. So what I try to do is I try to cover yang paling common lah, yang paling common, ataupun at least saya cover reaction yang kamu akan most likely jumpa in the real industry. So bila saya address reaction yang berlainan ni, sebab tu kamu tengok equation jadi pelik-pelik ataupun equation dia jadi kompleks. And then kalau kamu tengok soalan saya pun, soalan saya kenapa jadi susah ataupun kompleks, sebab actually the question that I give you are very common industry. Atau maksudnya soalan ni akan address isu-isu yang kamu akan jumpa dalam real reactors in the real industry. So I hope you understand why sometimes my questions can be very difficult, sebab kamu pun tahu nanti bila kamu keluar kerja, nanti kalau kamu pergi intern pun kamu akan perasan masalah yang dihadapi oleh engineer, technologists kat the real chemical plants are problem like this. So of course kamu tak akan ingat jalan penyelesaian dia, which is very common, tapi at least kamu dah pernah terbuka minda, exposed to at least certain degree of difficulty in solving problem. So I hope you understand kenapa reaction ni susah in that sense. I try to cover as much as possible when you join the real world, especially when it comes to reaction engineering. Okay, tu pun saya tak cover catalytic reactor. Kalau saya cover, I wish I can, but if I cover catalytic reactor, that's probably another 40, 60 or maybe 100 equation, which I can't afford to do so dalam 17 minggu ni. So I hope it give you a perspective kenapa kadang-kadang benda ni jadi sangat susah for reaction engineering. Okay, alright, so come back to the questions here. Okay, the following is the gas phase decompositions of pure diethyl butyl peroxide to produce ethane and acetone. So imagine this is I would say this is artificial reaction to produce ethane and to produce acetone, of which they just decompose pure diethyl butyl peroxide. So even from the very first sentence, kamu ada banyak information yang kamu dah boleh guna dalam calculation. First, gas phase. So saya katakan kalau gas phase tu kamu kena betul-betul make sure you really understand the difference kalau dia adalah gas phase reaction. First information. Second, pure diethyl butyl peroxide. Apa maksud dia? Meaning masuk-masuk awal tu satu reactant, and reactant tu 100% of that reactant, meaning it also signify there are no other reactant and there are no other inerts or any kind of other compounds besides your pure reactant A. Your pure diethyl butyl peroxide itu adalah kamu punya A. And then produk kamu ada dua produk. You have ethane, you have acetone. Okay, so you see from one sentence that sounds general, but it affects your calculation in many ways. Meaning, kalau kata pure A, YA naught tu satu. Okay, so that's the only information, that's the information yang dia nak lah. Dia kata pure tu maksudnya YA naught kamu 100% or 1. Right, so the question says, reaction carry out isothermally in a flow reactor. So kamu dah kena faham, kalau gas phase, flow reactor, check dalam notes dah berlainan dia punya equation. Second, dia kata isothermal. Okay, so tak apa. Setakat ni kita belajar memang semua isothermal. We don't have to worry so much. Nanti chapter 6 kita baru bimbang pula kalau ada isothermal. Okay. The pressure is 6 atm initially, but there is a pressure drop of 2 atm during the reaction. Okay, so apa maksud ayat ni? Dia kata, pada awalnya, yang diethyl butyl peroxide ni, okay, the pressure is 6 atm. Maksudnya P0 6 atm, but ada pressure drop of 2 atm. Ada kejatuhan tekanan sebanyak 2 atm. Maksudnya P naught 6, yang mula-mula masuk the pressure was 6, but after the reaction the P is now 4 atm. Kenapa 4 atm? Sebab dia kata mengalami kejatuhan tekanan sebanyak 2 atm. Okay, so kamu kena faham ayat ni betul-betul. Okay, kejatuhan tekanan sebanyak 2 atm maksudnya tekanan yang keluar selepas tindak balas adalah 4 atm. So P naught 6, P 4. Okay, so that's the second information. Means sekarang kamu tengok dalam notes pula. Okay, dia adalah liquid phase, this a gas phase flow reactor with pressure drop. Tapi tak cukup lagi nak cari, still not enough to find desired equation sebab tak tahu rate law lagi. Kan saya dah kata nak cari equation kena tahu 3 benda. Reactor dah tahu, fasa dah tahu, gas. Okay, 3. Rate law kita tak tahu lagi because they haven't told us the rate law yet. Okay, so tak boleh carilah desired equation lagi. Okay, so next sentence baru kita rate law. Rate law dia adalah reaction is second order with respect to dilute butyl peroxide. Okay, so now baru dia bagi information pasal reaction order. And then dia kata reaction ni second order with respect to A. Dilute butyl peroxide tu our A, right? So our minus our A is equals to KCA square. So automatically kamu tahu kan, kalau reaction order dah tak ikut persamaan kimia, this is non-elementary reaction. Sebab tu kalau non-elementary reaction, dia tak terus non-elementary pun tak apa. Tapi dia terus bagi reaction order tu kamu ikut sahaja. Meaning to say, ni dah confirm bukan elementary reaction. It's no longer elementary, it's non-elementary and that's why they give us the rate law. So dah dapat 3 information ni, baru kamu cari equation. Baru kamu akan tahu equation yang betul. Okay, so next. The feed rate of dibutyl peroxide is given as 379 million gram yearly with a dibutyl peroxide initial concentration of 5 mole per liter. Okay, so information ni kata next, they give us feed rate. Okay, so feed rate ni adalah how much A yang digunakan and how much A used is 379 million gram yearly. Means setiap tahun dia akan menggunakan sebanyak 379 million gram per year. Okay, so again, kalau kamu perasan dalam soalan saya banyak menggunakan production rate, feed rate and biasanya production rate, feed rate ni saya guna dalam bentuk mass. Sebab dalam real industry pun, when they talk about production rate, feed rate, most of the time dalam bentuk mass per year. Sebab tu kalau soalan saya akan guna feed rate ataupun production rate dalam bentuk mass. Sebab most of the time when we talk about production rate ke, feed rate ke, normally people will report in terms of mass per year. Sebab tu dalam soalan pun saya buat macam tu, mass per year. Means nanti kalau when you go to the real world, kamu kerja, kamu tahulah macam nak convert. So I include that as an element in the question so that you know how to convert from mass feed rate kepada molar feed rate, let's say. Okay. And then dia kata CA naught, initial concentration 5 mole per liter. So dia beri kita yang feed rate ni, kalau kamu perasan, kalau kamu confused, saya saja kamu. Gram ni mass, year ni time. So mass per time actually adalah mass flow rate. Actually anytime per time akan jadi rate. So bila dia adalah mass, gram tu mass, mass per time dia jadi mass flow rate. Okay, so memang diberi kita mass flow rate. Tapi mass flow rate pun kamu kena faham. Dia spesifik kepada compound. And then dia juga spesifik inlet ke outlet. So since dia kata feed, so kamu tahu initially lah kan. So initially mass feed rate A. So mass feed rate kita biasa guna M. So patutnya dia bagi kita MA naught. Okay, initial mass yang digunakan MA naught adalah 379 gram per year. Okay, done. So dia kata dia suruh kita cari the volume of a single PFR and a CSTR to achieve 95% conversion. So dia suruh kita cari separately volume PFR dan volume CSTR kalau diberi conversion 95%. Okay, so again, kalau kamu nak start soalan untuk chapter 4, macam saya kata, kita cari dulu equation yang akan digunakan. If let's say you really don't know nak start mana, tengok dulu equation apa yang akan digunakan. Sometimes from there, kamu akan dapat idea macam mana kita nak solve. Okay, so kamu dah berjalan cek tempat kan? Again, kamu ingat 3 benda ni. Okay, phase, gas, PFR or CSTR. Third, rate law dia minus RA KCA square. And then kamu tengok dalam note saya ada tambah satu part di mana saya address kalau ada pressure drop. Okay, make sure kamu tengok juga sebab sekarang tambahan benda yang keempat, pressure drop pula. Okay, so again kamu kena tengok betul-betul. So when you see properly in my notes, okay, dia ada dua equation yang berlainan lah kan. So equation pertama untuk volume CSTR. Okay, so kamu tengok ada tambahan part yang P0 per P tu sebab perubahan tekanan. Okay, the second equation untuk CSTR sama je. So kamu tengok dalam note saya, again ada address perubahan tekanan. Okay, kejap saya tengok something here. P per P0. Okay, kejap. I find something is weird here. KCA0, saya rasa macam terbalik. KCA0, pressure drop, 1 plus epsilon X. Salah. Okay, now I know what's wrong here. So this one is wrong. By right, 1 plus epsilon. This is, okay, ni salah note saya, apa saya dah. Okay, alright. So kenapa saya kata salah tadi? Sebab saya ingat dia punya equation ni, P0 ni dia akan berpasangan dengan 1 plus epsilon X. Maksudnya, kalau 1 plus epsilon X kat atas, P0 tu mesti kat atas. Tadi saya tulis P kat atas, P0 kat bawah. Tu saya rasa pelik sebab I always remember, kadang-kadang saya confuse juga part P per P0 ni. Tapi saya always remember, P0 ni pasangan dengan, dia mesti sama level dengan 1 plus epsilon X. So kalau 1 plus epsilon X kat atas, P0 tu confirm kat atas, dia tak boleh kat bawah. So this is correct. So sama juga. The P ni berpasangan dengan K. So P kat bawah, K kat bawah, K kat bawah, P kat bawah. Okay, betul. So these two equations are already correct. Okay, saya tak pasti dalam notes saya buat betul tak. Dia check balik dalam notes. I'm not sure whether my notes are correct or not. I will check back my notes. I think it's correct in the notes, but I will check back. Okay, so let's say now you have these two equation already. Kita nak cari volume. Okay, so sekarang kita kena tengok one by one lah. All the unknowns that we need to solve first. So first of all, kita solve. Let's say kita buat dulu PFR. Okay, kita buat PFR. First thing first is FA0. Okay, so part pertama pun, kalau kamu perasan dalam soalan, FA0 is inlet molar flow rate. Kalau kamu perasan dalam soalan, we don't have inlet molar flow rate. We do have initial concentration. Okay, we do have CA0, but we don't have FA0. Okay, you may say that kan ada perkaitan FA0, CA0 dan V0, meaning to say if I know V0 dan CA0, saya boleh cari FA0. True, but in this question pun, V0 is not given. Inlet volumetric flow rate tak diberi. Kalau kamu perasan, tak ada sebarang nilai dalam unit volumetric volume per time. Tak ada sebarang maklumat volumetric volume per time. So inlet volumetric flow rate tu tak tahu. Okay, so saya lupa nak touch bahagian additional information. Sorry, in the question there is additional information. Tapi additional information dia first is K, kedua molecular weight, and ketiga adalah dia punya plant punya operating time. So confirm inlet volumetric flow rate tak ada. So kamu tahulah, maknanya nak cari FA0 menggunakan V0 dan CA0 dah tak boleh. Tetapi again, there's a reason why dia beri kita mass flow rate. So kamu sudah tahu kan, mass nak tukar kepada mole guna molecular weight. So mass flow rate nak tukar kepada molar flow rate pun boleh, still using molecular weight. So since we don't know FA0, but we know MA0. Kita tahu inlet mass flow rate of A, MA0. So if I know MA0, I can change to FA0 using molecular weight. So soalan saya ada few soalan yang saya dah pernah touch part ni kan. Kamu dah tahu macam mana nak convert. Basically your mass flow rate, you divide with the molecular weight to get your molar flow rate. Tetapi be very careful regarding the unit time. Okay, tak. Saya tahu gram nak tukar pada mole senang je kan. Bahagi molecular weight dah dapat dalam bentuk mole. Tapi unit time tu sebab mass flow rate, unit kita was year. Okay, tapi kita fikir apa unit time yang kita nak guna. Sebab mass flow rate kita unit dia adalah gram per year, right? Can we maintain the year or not? Okay, so kalau saya jadi kamu, I will always again check back information yang diberi, especially information yang ada unit time. Okay, so the only information yang ada adalah sebenarnya nilai K saya, which the nilai K unit is minute. So I will use that basis, meaning my time yang tadi year tu, I will convert to minute. Tapi to convert from year to minute, kamu kena faham dia bukan straightforward sebab it has to follow the operating condition or the operating time of your plant. So meaning to say, contohnya dalam soalan ni, okay, in 1 year, the plant from you to convert from year to minute, kamu dah tak boleh direct sebab in 1 year, although we have 365 days, but this plant only operate 360 days. So, kamu kena convert dulu kepada days. So, 1 year, 360 days. Okay, then next. Although 1 day you have 8 hours, but the plant although 1 day has 24 hours, but this plant only operates 8 hours. So kamu kena convert pula daripada year to day, day to hour. So conversion time tu kamu tak boleh guna standard conversion time yang kamu pernah belajar yang says 1 year 365, 1 day 24 hours. Not necessary sebab operating condition ni bergantung kepada your plant. Okay, so then from hour you change to minute. Yang tu yang betul lah. 1 hour mesti 60 minit lah kan. Okay, so you change. Eventually you get your FA naught as 15 mole per minute. Okay, so this part kamu kena faham lah bagaimana from mass flow rate. We change to molar flow rate first. Second, making sure the unit times are consistent. Okay, some might say, katakan saya nak maintain year, unit K ni saya tukar daripada minit kepada year. Boleh je, sama je. Your final answer will be the same. Asalkan make sure unit time kamu tu semua consistent. Sebab saya kata reaction has no one standard method. Katakan cara saya tukar FA naught dalam bentuk per minit. Katakan kamu tak nak, kamu nak maintain per year. Okey je, tapi kamu jangan lupa yang unit minit dalam K ni, you have to change to year. If you don't change to year, then salah lah. And then kamu nak change to year, kamu kena tengok balik. Sama je, kamu kena consider operating condition of the plant. So either one you do, either you change the K or you change the FA naught. Final answer is still the same. Okay, alright. So done on the FA naught. Okay, so next kat bawah dia K dah diberi. So you don't have to find the new K because they do not state the K is at what temperature and they don't state in the question as well temperature dia. So you may assume K yang diberi adalah at your reaction temperature. So K, you use the K given. CA naught was given in the question 5. So CA naught pun settle. Okay. So P naught per P ni yang tadi kita discuss lah. Initial pressure 6 atm. Pressure drop off 2 atm. So jadi 4 atm. So 6 per 4. 6 atm per 4 atm. Okay. Then next, in bracket ni, apa yang panjang ni kena carilah one by one. Okay. So first epsilon. So epsilon ni mungkin kamu tak biasa cari sebab kita jarang address question yang ada gas phase kan. So kalau kamu lupa nak cari epsilon, epsilon ada formula, ada sub formula. Epsilon equals to YA naught sigma. Kalau kamu lupa pun tak apa, kamu check note chapter 3 kalau kamu forget this part. So epsilon is YA naught sigma. YA naught tu adalah apa? Initial mole fraction of A, which is 1 because dia kata pure A. Kadang-kadang kamu tengok ayat dia pure A. So tapi pemahaman dia dalam pengiraan, oh maksudnya YA naught tu adalah 100%, YA naught is 100% or in fraction, YA naught tu 1. Okay. Next, sigma. So sigma ni pula ada pula sub equation. So nak cari sigma ni, sigma kalau kamu lupa is the ratio of stoichiometric coefficient. But this ratio ni ada positif, ada negatif depending on the role of species in the reaction. So dalam reaction ni, dia ada satu reactant, dua produk. Okay, A is a reactant, B and C is a product. Hence, it is positive stoichiometric coefficient for the B and C as a product and a negative stoichiometric coefficient ratio for A. So, dia menjadi plus B per A plus C per A. Of course, pas kat depan kita tak tulis kan. So, kita sebagai B per A plus C per A minus technically A per A which is 1. That's why dia akan sentiasa minus 1 sebab minus 1 tu sebenarnya adalah minus A per A. So B per A, equation dia B per A is 1. From the stoichiometric coefficient kamu nampak satu A, satu B, satu C kan. So B per A is 1. C per A is 2, sorry. C per A, C kamu ada 2 di hadapannya. So C per A become 2/1. Tengok kadang-kadang saya pun tersalah tengok stoichiometric coefficient. So make sure you tengok properly stoichiometric coefficient dia. So C per A is 2/1 minus 1. You got your epsilon as 2. Okay, so epsilon ni as I said dia boleh jadi negatif, tak semestinya positif. Dia boleh jadi negatif, but in this question jadi positif lah. But let's say tak semestinya positif. It may be a negative number. Okay, so dan epsilon. So X pun kita dah tahu, X was 0.95. So basically you have already solved everything. Okay, again when you have extra time, please make sure you calculate by yourself sampai dapat jawapan akhir ni sebab most of the time kita tengok macam boleh solve sendiri tapi bila kamu tekan calculator very likely kamu tak dapat jawapan yang sama. So by now you should practice to calculate by yourself using calculator, tengok dapat tak jawapan akhir dalam seperti yang diberi oleh saya. Okay, so then next CSTR. So CSTR pun sama. Kamu tengok balik note. Okay, kalau ada CSTR, gas phase minus RA KCA square and pressure drop. Nombor keempat ni kena ingat. Pressure drop, equation ni diberi dalam bentuk yang saya highlight ni. So information semua masih sama. FA0 masih sama, X is the same, K is the same, CA0 is the same. Okay, P0 per P is also the same. You replace, you will get the volume of your CSTR. So that's how we solve the problem to find the volume of PFR and CSTR. It is not too difficult, but make sure you calculate by yourself to see whether you dapat ke tak dapat. Okay, so again, I give you 1-2 minute break. So why not, if you are free, you have a calculator in front of you, I'll give you 1-2 minute break while I take a little bit of short break. Kamu cuba tekan untuk PFR ni, kamu tengok dapat tak jawapan akhir sama dengan jawapan akhir saya. Sebab kenapa saya suruh try? Sebab equation ni ada bracket, sub bracket, ada ln, ada tambah, ada tolak. So I would like you to try by yourself. Sementara saya ambil short break, I will see you back in about 1-2 minutes time. So saya tinggalkan ni kat sini, kamu try tekan kalau kamu ada calculator. Okay, so I come back in 1-2 minute break. Okay, hopefully you did have the time to try, but if you cannot get the final answer, most of the time is sebab bila kamu tekan calculator tu, bracket tu sangat penting lah. So if you cannot calculate, kalau masuk sekaligus seluruh ni dalam calculator, you tend to make mistake. So macam saya, kadang-kadang saya kira parts by parts. Then saya combine baru dapat jawapan akhir. Okay, so that's one way lah. Of course, it's better kalau kamu masuk semua dalam satu calculator. Tapi you tend to make mistake sebab kalau bracket tu kadang-kadang kalau salah bracket atau tak cukup bracket atau bracket di salah tempat, the answer may not be accurate. Okay, so that's one of the tips lah kalau let's say you cannot get the final answer. Right. So last question for today, before we are done for today, kita touch satu soalan reversible. So reversible, saya tak pernah touch lagi. Contoh dalam notes pun saya tak touch sebab I ask you to try to do it by yourself. So I try one questions for today, for tutorial and then we are done. Okay, so reversible pun tak senang sebab tu. Kalau reversible, I will only teach you to design for CSTR sebab kalau saya nak ajar untuk design PFR dengan batch, it's very complex sebab dia melibatkan pengamiran kan. So pengamiran tu kamu faham kalau dia adalah reversible, dia akan jadi quadratic. No, maybe more than quadratic, the solution is too complex. But nevertheless, doesn't mean tak ada orang design reactor untuk PFR atau batch for reversible reaction. Okay, again I repeat, for my reaction ni pun saya cover reversible reaction untuk design CSTR sebab CSTR ni linear equation, tak kompleks sangat. Even that pun kompleks dah. Tapi kalau kita nak design reactors, if I were to teach you design reactors for batch and PFR for reversible, memang equation dia jadi menakutkan, memang sangat kompleks. But it is possible and the industry you will always see reversible reaction in batch or PFR. Okay, so let us try this question. The production of B is carried out in an elementary reversible reaction. Okay, so sama je. Reversible reaction ada elementary, non-elementary. Kalau non-elementary, rate law, equation dia akan, rate law dia akan diberi. Okay, kalau elementary, dia dah tak sama macam elementary irreversible. Elementary reversible berbeza dengan elementary irreversible. Meaning, kamu dah tak boleh tengok sebarangan stoichiometric coefficient dia. Tapi rate law dia ada specific rate law, which is, okay, saya cover sikit kat part ni. Okay. Rate law dia akan diberi sebagai, dalam notes pun ada, tapi saya repeat balik. Elementary reversible is given as minus RA equals to K. K tu mesti ada. Dalam bracket sekarang ada dua part. Okay, so part yang pertama ni adalah concentration of all of your reactant kuasa stoichiometric coefficient. Okay, dalam kes ni hanya satu reactant A and stoichiometric coefficient dia adalah 1. Okay, sebab tu kamu tulis sebagai CA. Okay, okay, saya untuk elakkan kamu keliru, kalau dia tak berbalik, kalau dia irreversible, tindak balas ke hadapan sahaja, memang kita akan stop kan pada minus RA KCA. Betul? Sebab dia irreversible. Tapi kalau dah reversible, berbalik, sebab tu ada part yang kedua kat belakang ni. Part kedua kat belakang ni untuk address bila tindak balas dia ke belakang pula. Yang part depan ni untuk tindak balas ke depan. Yang part belakang untuk tindak balas bila dia ke belakang pula. Sebab tu ada minus. Dia mesti minus. CBCC yang kat atas ni adalah concentration of your product, all of your product kuasa stoichiometric coefficient. So since B and C stoichiometric coefficient adalah 1, sebab tu minus CBCC. So part yang CB ni yang kamu kena berhati-hati. Dalam contoh ni, B is a product. Sebab tu B muncul di bahagian kedua. Tetapi kamu ingat kan, kadang-kadang dalam certain reaction, B can be the reactant. Kalau B tu reactant, perkataan B akan muncul di bahagian awal ni. So that's why saya kata dia tak boleh sangat menghafal. Kamu kena faham certain equation ni akan berubah mengikut the reaction. Okay, so again I repeat for CB, in this equation, as CB is a product, CB muncul di bahagian kedua. If CB is a reactant, let's say in other reaction, CB will comes together with CA. Okay, so done. Then divided by KC. So KC ni apa? Equilibrium constant. Okay, so this is how you write elementary rate law for reversible reaction. So dia bukan tak sama dah dengan irreversible. Kalau irreversible tu rate law dia hanya tengok yang ke hadapan sebab dia tak berbalik kan. Tapi bila dia adalah reversible, kita kena tengok rate law kita kena tengok yang ke depan dan juga yang ke belakang. Okay, so done on the rate law. So next one. Pure reactant A in the gas phase is fed to the system at a pressure of 5 atm. Okay, so apa information dia beri dalam this sentence? First, pure A meaning YA0 1. Okay, second, gas phase. So kamu kena faham ini adalah gas phase reaction. Next, dia kata pressure 5 atm. Feed to the system, pressure awal dia 5 atm. Means P0 5 atm. Reaction rate constant 500 per second, K 500 per second, equilibrium constant 0.5, so KC 0.5. Kamu dah kena faham, kalau ada reversible reaction, kita ada constant yang baru, which is equilibrium constant. So equilibrium constant tu adalah KC. Yang reaction rate constant K, dia lain. Satu pemalar kadar tindak balas, satu adalah pemalar keseimbangan. Pemalar keseimbangan KC is only for reversible. Kalau tindak balas irreversible, kita takkan jumpa KC. That's why kamu baru jumpa KC untuk case ni. Sebab KC specific for reversible reaction. Okay, so next dia kata, there is a pressure drop to 3 atm after the reaction occurs. Meaning, the pressure earlier on was 5 atm. Selepas tindak balas berlaku, pressure drop kepada tekanan turun atau jatuh ke 3 atm, meaning P0 5, P3. Kamu perasan tak beza dengan ayat sebelumnya? Ayat sebelumnya, soalan nombor 4 dia kata, there is a pressure drop of 2 atm. Maknanya ada kejatuhan tekanan sebanyak 2 atm. Means daripada 5 atm, dia jatuh sebanyak 2 atm, tekanan akhir 3 atm. Contohnya, dalam soalan ni dia kata kejatuhan tekanan kepada 3 atm. Meaning, it drops from 5 to 3. So, kamu kena beza ayat pressure drop off or pressure drop to. Okay, so dalam soalan ni P0 5, P3. Okay, so next. Determine the initial concentration of, initial concentration of A, 5 mole per liter, Ca0 5. Okay, so done. That's all information yang dia beri. Okay, this says, determine the equilibrium conversion of the reaction. This one kita cari the equilibrium conversion. So, kalau kamu lupa, saya pernah ajar kamu untuk tindak balas reversible, asal-asalnya bila tindak balas ni berlaku estetik. Reaction will goes forward, backward, forward, backward. So, maksudnya bila tindak balas ni berlaku, sebelum dia mencapai keseimbangan, kamu akan tengok dia punya concentration produk dan reaktan ni berubah-ubah. Sebab kalau tindak balas ke hadapan tu lebih cepat, banyak produk. Katakan tindak balas ke belakang tu lebih cepat, banyak reaktan, so on and so forth. But eventually, they will reach equilibrium. Maksudnya pada equilibrium, kepekatan ke semua compound berada pada kepekatan yang sama, dia dah tak berubah. Okay, so at this condition, at this equilibrium concentration, conversion yang dicapai adalah equilibrium conversion, and that is the highest possible conversion dalam reversible reaction. Means reaction tu dah takkan mencapai 100%. Kalau 100% tindak balas hanya ke hadapan. Tapi sebab dia ada ke hadapan ke belakang, that's why equilibrium conversion is never 100%. Unless kamu kacau sistem untuk naikkan, yes. But if you don't disturb the system, the highest possible conversion is your equilibrium conversion, which we put it as XE. Okay, so macam mana kita nak kira XE kan? Alright. So kamu kena tahu dahulu. Kita boleh kira XE you know that equilibrium conversion mesti pada keadaan equilibrium. So the only information yang ada kaitan dengan equilibrium adalah sebenarnya equilibrium constant. Kalau kamu perasan kan, maklumat lain tak ada berkaitan dengan equilibrium except at equilibrium constant. And we know that equilibrium constant ni kita boleh cari menggunakan concentration of the reactant pada equilibrium. Sebab equilibrium constant tu adalah nisbah kepekatan reactant kepada produk at equilibrium. Ataupun in this term, we can write it as Kc equals to product C and B. So concentration of B and C at equilibrium, kuasa stoichiometric coefficient, itu pun kena ada. Kuasa stoichiometric coefficient itu follow the chemical equation. So why I put it as E? E untuk kedua B and C sebab kepekatan ni mesti measured at equilibrium. So CBE, CCE divided by CAE, concentration of your reactant at equilibrium, power stoichiometric coefficient. Okay, so I've written it properly, but you may ask, tapi dalam situasi ni tak ada XE kan? Belum ada XE lagi. Kita nak cari XE. Tapi pada part equation ni, there's no XE yet. Okay, so that's where come your knowledge. Kamu dah pernah belajar. Kita tahu perkaitan antara concentration, outlet concentration and initial concentration and X. Tapi part ni kamu kena careful sebab expression dia dah jadi kompleks sikit. Okay, apa maksud saya kompleks? Kamu pernah belajar dalam chapter 3. Kalau part ni kamu rasa macam pelik gila, you have learned in chapter 3 tapi kita belajar bukan untuk equilibrium. Kita pernah belajar kalau gas phase flow system, okay, again gas phase flow system, CAE sama dengan CA0, CA. E tak ada lagi kan? Kita belajar yang part CA dulu kan. So CA equals to CA0, 1 minus X per 1 plus epsilon X. And ada perubahan tekanan kena tambah. Ya, ada soalan ke? If someone has a question? Tak ada. Kita buka. Alright. So the question will have P per P naught. Okay. So kamu pernah belajar equation ni dalam chapter 3. Kalau kamu tak dapat catch up part ni, chapter 3 part yang gas phase expression, express concentration for gas phase. Ada part ni. Okay, so then next, apa beza dia? Sebab kita cari sekarang concentration in terms of equilibrium. Sebab tu conversion ni akan menjadi equilibrium conversion. If you ask, kenapa part lain dah tak tambah equilibrium? CA0 tak akan berubah. CA0 adalah kepekatan asal. Pada equilibrium tak ada equilibrium pun, kepekatan asal yang kita prepare will still be the same initial concentration that we prepare. Okay, P per P naught ni pun sama, equilibrium dan equilibrium. P per P naught ni akan sama. Just that conversion tu yang akan berbeza sebab conversion tu will be evaluated of which the concentration of your A, B and C at equilibrium. Okay, since kita nak cari XE, meaning we can leave the XE, the rest we will replace with number. Okay, so similarly for CBE, CCE pun sama. Okay, so again kalau kamu perasan dalam notes, part ni saya admit memang susah sebab notes chapter 3 saya, I do express the first part tapi saya tak include part yang pressure drop ni dalam chapter 3 punya notes. Sebab part ni kamu dah kena faham dalam chapter 4 pula. Kalau ada pressure drop, apa yang akan berubah pada kepekatan. Okay, so if you find from note chapter 3, memang tak ada part yang P per P naught. Tapi dalam chapter 4 kamu dah belajar. Kalau part ada tambah perubahan tekanan, apa yang berubah dalam equation. Sebab tu kamu kena faham, dalam note saya impossible untuk saya include semua. Tapi you have to somewhat correlate what you learn in chapter 3 and what you learn in chapter 4 to form the equation. Okay, so next. Once kamu dah tahu to express A, B and C at equilibrium in the form of XE, kamu replace dekat dalam. So this is also a very complex quadratic equation sebab dah ada, ni ada 4 layer lagi. Layer kedua di atas, 2 layer di belakang bawah. So this part, okay, again, when you have free time, please learn how to solve this. You will get the equilibrium conversion as 37%. So a very low equilibrium conversion actually. Okay, so it's 37%. Right, so done for part A. Okay, so part A, It a bit complex. So kalau kamu tak faham, kamu kena betul-betul check lah notes chapter 3 combine dengan notes chapter 4. In my notes also part reversible ni saya ada address satu question yang hampir sama macam ni. Please read lah to further understand. Bukan further understand lah, to do the calculation. Okay, alright. So last part for today. Okay, so ni. Calculate the CSTR reactor volume if the given conversion of A is 95% of the equilibrium conversion with initial rate of 50 liter per second. So soalan ni sekarang dia kata, they ask us to find the volume of CSTR if conversion dia 95% of the equilibrium conversion. Apa maksud ayat ni? Okay, sekarang kamu dah kena faham pula. Conversion ni, okay, ni yang part yang mungkin student get be confused. Okay, equilibrium conversion is the conversion when it reach equilibrium. Okay, tetapi bila kita design reactor, okay, bila kita talk about reactor punya conversion, dia tak semestinya menggunakan equilibrium conversion. Most of the time, we will use less than equilibrium, definitely less lah kan, cannot more because equilibrium conversion tu adalah maximum. We will use less than the equilibrium conversion. So means bila kita nak kira conversion reactor tu X. Okay, X ni akan yang kita nak guna pengiraan adalah not the same as equilibrium conversion XE. Okay, so dalam soalan ni dikata conversion reactor saya, X saya, dalam reactor saya punya X adalah 95% of my XE. Dia bukan conversion 95%. Conversion tu adalah 95% daripada equilibrium conversion saya. Means 0.95 multiply with my XE, which is 0.37 from the first part. So my reactor real conversion is 0.3515. So again, I repeat, most of the time reactor punya conversion bukan conversion equilibrium, XE. So X is not XE. So we have to determine lah, ataupun kita kena set lah berapa conversion yang kita nak dalam reactor kita. So in this case, the reactor conversion is stated as 95% of my equilibrium conversion, which is XE from the first part calculation 0.37. Hence, my X will be 0.95 multiply with 0.37, you get 0.3515. Itu adalah conversion dalam reactor saya. Okay, so that's information that they want. So now they ask us to find the volume reactor. So volume reactor ni kamu kena be very careful. Kenapa? Okay, so kita dah pernah belajar volume CSTR equals to FA0X per minus RA. So minus RA tadi saya dah terangkan rate law dia elementary reversible reaction. Rate law nya diberi dalam bentuk yang font merah ni. So minus RA tu kita replace dengan K in bracket CA minus CB/CC per KC. So kita nak cari volume kan. So means on the right hand side everything has to be replaced with numbers. So first of all FA0. So FA0 dalam case ini, they do give us, they give us a CA0 and they give us a V0. Dia beri kita V0 50, CA0 5, you can find FA0. Okay, so FA0 akan jadi CA0 multiply by V0 lah. So kamu tengok sini saya tulis CA0 multiply with V0, this is FA0. Okay, so done. FA0 dah settle. X tadi yang 0.3515 settle down K, so K is given as 500 per second dan CA, CB, CC. Okay, kalau dalam case CSTR, sebab dia bukan integration, kamu boleh cari dahulu CA, CB dan CC baru ganti dalam persamaan. Sebab kalau kamu nak express dulu, masuk dalam persamaan tu jadi sangat kompleks. So you can actually calculate your CA, CB, CC first. Okay, so part ni pun you may get confused. Part awal kita dah pernah express concentration kan, tapi concentration yang part atas ni pada equilibrium. That's why we write as CAE, CBE, CCE. Tapi bila kita design reactor, let's say kita takkan design reaktor pada equilibrium, maka kepekatan dia pun dah bukan pada equilibrium. That's why we write it as CA, CB, CC. So conversion pun dah bukan equilibrium conversion. Conversion yang tadi yang kita kira tadi, yang baru tu, yang 0.3515. So that's why the X here is no longer XE. Okay, so again I repeat, bila kita design reaktor, kita tak guna kepekatan pada equilibrium. Okay, we will use concentration at the conversion of our reactor, which yang kita kena tahulah. So dalam case ni, conversion dia adalah 0.3515. So yang part lain, P per P naught semua masih sama. So you will calculate CA, CB, CC dahulu. Again, untuk case CSTR tak apa sebab dia equation linear. Kamu boleh kira dulu masuk dalam pun tak apa. Okay, so when you calculate, you replace inside CA, CB. So happen both CB, CC, you will get the same concentration. So you replace and you replace KC, you will get the volume of the CSTR. Okay, so before I forget, okay, part S plus concentration ni kamu kena faham kenapa dia menjadi bentuk ni, sebab dia adalah gas phase flow reactor. Okay, so katakan kalau soalan dia bukan gas liquid phase flow reactor, kamu kena faham macam mana equation dia akan jadi. Okay, again I repeat, why this equation is like this is because this is gas phase flow reactor. So kamu kena faham juga kalau concentration untuk liquid phase macam mana. So notes chapter 3 saya ada address part ni. Right? So that's all for today. So I can understand the questions are quite tough today. 4, 5, 6 is a bit tough. Tak apa, nanti bila you have time, just go through again. It's better if you can go through again if you have time and tengok notes sekali. So kamu akan faham part mana notes yang berkaitan, lecture notes, part mana yang berkaitan dengan soalan yang saya solve for today. Okay, so I will see you back in 30 minutes for our lecture. We will continue lecture chapter 5 and I'm done for tutorial today. So thank you very much everyone. See you back in 30 minutes.